The branch of physics known as mechanics was well developed by the beginning of the 1800s. It was possible to describe motion of objects and particles with high precision, and there were also well-developed techniques for describing the behavior of waves, such as sound and light. But at the beginning of the 20th century, some experimental observations were made that really shook the field of mechanics and physics as a whole to its core. And these observations boil down to the idea that waves can behave like particles and particles can behave like waves. In this video, we're going to be looking at the first part of this and the way that it relates to light. Now, when you think about light, it's easy to envision light as beams of material that stream through things like windows. And indeed, Isaac Newton propounded a corpuscular theory of light. He believed that light consisted of particles that travel in straight lines through space, and probably part of Newton's motivation was that, along with Gottfried Leibniz, Newton had developed the calculus in mathematics, which was aimed at describing motion of particles and planets and things like that. And so it was, I suppose it was only natural that Newton would try to apply his ideas to light. Now, at the same time that Newton was describing light as particles moving through space, a Dutch mathematician named Christian Huygens proposed a description of light on the basis of waves. And it wasn't really until the 1800s that experimental results could really settle the matter and demonstrate that, for the most part, light did seem to be act in a wave-like way, and this was further developed at the end of the 1800s by James Clerk Maxwell, who developed an electromagnetic theory of light, which described light as a disturbance in the electromagnetic field. And this was a highly successful theory, and one of the important ramifications of the theory was that matter and light interact with each other very closely. And in particular, it was known that if you accelerate a charged particle, like an electron, the accelerated particle emits light. And this light can travel through space, and if the light hits another charged particle, it can accelerate that particle and induce things like electric currents. And this is the basis for technology like radios. These guys testing out their radio set would be able to accelerate electrons in an antenna. Those accelerated electrons would generate radio waves, which could then be picked up by these other guys with their own antenna. So this connection between light and matter is very strong and very important. And I want to look at light that's produced by matter, not in an antenna, but light that's produced by matter just when you heat it up. And this kind of radiation is called blackbody radiation. Now, a blackbody, as the name implies, a blackbody is an object that is perfectly black in the sense that it absorbs all colors of light, all wavelengths of the electromagnetic spectrum. And no real object is a perfect blackbody. Any real material will absorb some frequencies more than others. But if you were to make a box with a small hole in it, then light entering the box will bounce around, and if it bounces around enough times, all the frequencies of light will have a chance to get absorbed, and such an object is is very nearly a perfect black body. Now, you can't achieve a perfect black body without having the object be infinitely large and having the light bounce around an infinite number of times. But you can achieve things that are pretty close to the black body ideal. And even just ordinary objects can behave as black bodies when you heat them up. In addition to absorbing radiation of all frequencies, black bodies also emit radiation of all frequencies. And if you take a chunk of matter like this lava and heat it up to a high temperature, 1,000 kelvins is equivalent to about 700 degrees Celsius. If you get any piece of matter hot enough, it will emit light, and the pattern of light that it emits is fairly close resemblance to blackbody radiation. And if you were to heat matter up even hotter, then the pattern of light changes, but it still matches the blackbody pattern. Now, this is an example of blackbody radiation that corresponds to an object that's been heated to 3,000 kelvins, and that is about the temperature of a tungsten filament in an incandescent light bulb. And you can see that such a hot object emits radiation across a wide range of frequencies, and these frequencies extend into the visible part of the spectrum. You can see that the incandescent filament emits light mainly toward the red end of the spectrum, and this accounts for the sort of yellow-orangish appearance of an incandescent light bulb. But you can also see that most of the radiation that's emitted by the tungsten filament is in the infrared part of the spectrum. The emission does extend into the ultraviolet, but there's very little radiation emitted that far out in the spectrum of something like a light bulb. Now, one problem from a standpoint of physics is that the classical theory that was developed that described how particles move and how waves like light waves behave is classical theory predicts that an object that's been heated to a high temperature should emit light at all frequencies, but as you go to higher frequencies, the intensity of light should get higher and higher and higher. It shouldn't go up and then come back down the way it's observed for a real object, a real black body. The prediction matches observations for very low frequency radiation, but once you start moving into higher frequencies, there's a big deviation between what the classical theory would predict and what we actually see in the pattern of light emitted by a hot object. And this discrepancy, some people have described this as a paradox in the behavior of light, comes down to the fact that in the classical model of vibrating atoms and the wave behavior of light, the energy associated with a wave like a light wave depends on the frequency of the wave in units of cycles per second or hertz. It also depends on the intensity. And the idea in the classical mechanics was that an object like a black body was able to get excited at all frequencies, and each frequency would have the same amount of energy. And so what that meant is that light, a vibration or a motion at a low frequency would be very intense, would have a high intensity, and motion at a high frequency would have a very low intensity. But the important thing is that the intensity could have any value. You could have waves that had very low intensity, in other words, very dim, or you could have waves that had very high intensity, very bright, and anything in between. There was a continuum in intensity that was allowed by the classical model. And now what happened was, in 1900, a physicist named Max Planck showed that you could describe the distinctive pattern of blackbody radiation if you assumed that instead of this classical model where the intensity of the wave could have any value, you could explain blackbody radiation with a quantized model in which the energy of a wave was restricted to certain values. And again, the energy depends on the frequency, nu, and depends on a physical constant, which was named Planck's constant in honor of Max Planck. The numerical value of Planck's constant is 6.626 times 10 to the minus 34 joule seconds. And then you could have any multiple of that h nu. So n could be 1, 2, 3. And so in this quantized model, something like a vibration in a black body could only be multiples of sort of a fundamental wave. So you could have a wave with an energy of h nu. You could have another wave that's more intense that has an energy of 2 h nu. You could have 3 h nu, but you couldn't have 0.5 h nu or 1.6 h nu. You could only have multiples of this quantity, and this was able to explain blackbody radiation. And the reason that it explains it is that in a blackbody or in an object that's very hot, for low frequencies of motion, the amount of energy in this wave is very low, and so it's easy to achieve that amount of energy. But as you go to higher and higher frequencies, it becomes harder and harder for the object to get enough energy to even make the first wave with n equals 1. And so this quantization of the energy is able to explain blackbody radiation. And so sort of the physical picture that this creates is that motion in a blackbody that is responsible for emitting light is not can't change continuously, so it's not governed by something like a dimmer switch. Instead, it is multiples of a certain unit, and so it's more like a counter. You can have 1 unit of motion, you could have 2 units, 3 units, and so forth. And now Planck's model was extremely successful in describing blackbody radiation, but he had no idea why it was true. Basically, it fit the observations very well, but he and other physicists didn't understand where this pattern came from. Now, around the same time, observations were made of a phenomenon called the photoelectric effect. And in this phenomenon, a material such as sodium metal can be exposed to light, and when light falls upon the surface of the metal, once in a while an electron will be ejected from the surface of the metal. And if you shine brighter light on the surface, more electrons will be ejected, but they'll all have the same energy for a given color of light. If you shine light that has a higher frequency, like going from green to blue, electrons are kicked off, and they have more energy. And if you were to shine a bright blue light, more electrons would be kicked out, but they would have the same energy as with the dimmer blue light. And if you went in the other direction, if you shined red light on a chunk of sodium, nothing would happen. You wouldn't see any electrons coming out. And it doesn't matter how bright you make that red light, electrons are never going to come out of the sodium metal. And so Albert Einstein in 1905 realized that you could explain this puzzling phenomenon if you apply Max Planck's idea of quantized energy. And specifically, Einstein suggested that bright light, or that light is basically carries packets of energy, and that bright light just corresponds to multiple energy packets. And so the idea was that when one of these energy packets hits a chunk of metal, there's a chance that it would kick out an electron. And if you had more of those energy packets coming in with a brighter light, then there'd be more electrons would be ejected. And so the relation or the connection that Einstein proposed in his 1905 paper was that this quantization of energy that Max Planck developed to describe a black body actually applies to light, and specifically the energy of one of these packets of light is equal to h nu. H again is Planck's constant. Nu is the frequency, and so different frequencies of light will carry different amounts of energy in their packets. And the term for a packet of light came to be known as a photon. And so the energy of a photon of light is equal to Planck's constant times the light's frequency. And so this notion that light travels in packets of energy really shook physics to its core, because it had been believed that particles and waves were two completely different things, and the behavior of black bodies and the experimental results of the photoelectric effect demonstrated that light, even though light does act like a wave, it also is able to act like a particle. And so there became this notion of wave-particle duality, where waves could behave like particles, and as we'll see soon, particles can also behave as waves. And that wraps up this discussion for the moment.